Okay, we are going to finish our quadratics review today, starting on page 19. We're going to talk about interpreting points from a graph. We did this with linear functions already, so this should look familiar. The difference will be, again, that instead of lines, we're looking at parabolas, since we're talking about quadratic functions. Number one should look familiar because we actually worked on that problem. That was the last thing that we did last time. We're looking at our rectangular field that we are enclosing with some fencing. Okay. And we know we're looking at the width and then the area of our field. And so this is the same table from yesterday. The first thing it wants us to do is write a model. Again, we did this yesterday, so I'm going to steal our model from yesterday. Save us a little work here, which we wrote based on our vertex. So we wrote vertex form, x minus 50 squared plus 2,500. And we said our lead coefficient had to be negative because looking at the y values, the vertex y value was bigger than the surrounding y values. So that's our same function when we looked at this problem last time. And then B says, what's the vertex of your parabola? Well, I know that already. I know that my vertex is 50, 2,500 because that's what we use to write our function. Now, we can and we will graph this here in just a minute. We could get the vertex from the graph if we wanted to, but we already identified it in the table last time. So I'm going to use, again, that information that we worked with last time. So our vertex is 50, 2,500. 50 represents the width of our field. 2,500 represents the area enclosed by that. The piece that I want to make sure I address when I talk about describing the vertex in the context of the problem is that one, give labels to each of these, but two, since this is the vertex of the parabola, that means that this is the greatest area we're going to see. Again, we talked last time, about how that y value for the vertex is greater than the y values around it. So my parabola opens down. That means that this is actually the greatest area that we can have. So that is a slight change from when we talked about linear functions. Linear functions don't have a maximum or a minimum, but parabolas do, quadratic functions do. So when I'm talking about it, I want to make sure I mention that this is the maximum or minimum value for whatever that y component is. So I will say that the greatest possible area is 2,500 if the width is 50 meters. Oh, and I should put my label on here, meters squared. Then part C says find and interpret the x-intercepts. So I'm going to go ahead and pull up my calculator here and graph the function that we've created. So be careful when you type this in. X minus 50 squared plus 2,500. Now, when I graph this, I don't see a parabola. I got that little like blue flash for my graph right along the y-axis, but it definitely does not look like a parabola. So remember, we need to adjust our zoom. So menu, window zoom, and I like zoom fit as a starting place because it scales my graph. Now in this case, zoom fit still isn't giving me the best picture. I can kind of sort of see how it's starting to curve a little bit, but I'm gonna need to zoom out a little bit from here. So zoom out. I want the center of my graph to be here-ish. And one more should get us there. There we go. I'm going to go ahead and move my function label out of the way here because I know I want it to show me my x-intercepts. And now that I can see both of my x-intercepts, I'm going to have my calculator find them for me. So menu, go down to analyze graph, and I'm going to find the zeros of this function. So remember we did this last time, we click on either side of where we see those x-intercepts, and I can only find one at a time, so we'll have to do this twice, one for each x-intercept here. So I get 0, 0, and 100, 0. Now, the y value being 0 for both of these is referring to the area. The x value is referring to the width of our rectangle. So if our width of our rectangle, we're not talking about the length, so I want to address this 0 first. If our width of our rectangle is 0, that means we have essentially just put a line of fencing in, right? Our length is whatever it is. If our width is 0, that's just a fence. I haven't enclosed anything, and that's what this was supposed to be, right? This enclosed area. So I don't know if it was for like animals or kids or just to keep the kids away from my lawn or whatever the situation is. Just a line of fencing isn't doing me very good. And then the 100 must be the other option where our line of fencing goes this way. Our width is as big as it can be, but our length would be 0 there. So it's a line of fencing running the other way through my property, which again, not super helpful when we're talking about enclosing an area. So my x-intercepts here would be, or would mean that a rectangle with a width of 0 meters or 100 meters will have an area of 0 meters squared. I'm not actually fencing in an enclosure. I'm more just putting up a fence to put up a fence in that case. Questions for me on number 1? Okay, number 2. Beth runs a 5K. As she runs, her speed increases, reaches a peak, and then decreases. This is represented in the graph below. Find and interpret the y-intercept in the context of the problem. Remember, when we're interpreting points, I want to make sure I include, no matter what the particular point is, I want to make sure I include information about both the x and the y at that particular spot. So the y-intercept, where we cross the y-axis, would be right here. That's the point 0, 0. Our y number represents our speed. Our x number represents the distance that we've run for this 5K. So my y-intercept is 0, 0. So our speed is 0, and we've also run 0 kilometers so far. In the context of our problem, what does that mean? If I think about a race, this is the start, right? We haven't started yet. This is the start. We're getting ready to run our race. So I could say Beth's speed is 0 kilometers per hour at 0 kilometers, or when she has run 0 kilometers, or at the start of the race. We're getting ready to run here. Part B asks me about the x-intercepts. So my y-intercept is also an x-intercept. The other one is down here. So my x-intercepts are at 0 and 5. And remember, x is distance, how far I've run. My speed at these points would be 0. We talked about how this first point is the beginning of the race. What's this last point? It's a 5K. So at 5 kilometers, I'm at the end of the race, right? So we could say Beth's speed is 0 kilometers per hour at the beginning and end of the race. So she's gonna start running. She just finished running. Then for part C, find the vertex and interpret it in the context of the problem. So our vertex looks like it's here. That would be 2.5, comma 10. Remember, the x is the distance that we've run. The y is our speed. Since this is the vertex, we talked about this with our last problem, and the vertex is the maximum on our graph. That also means that this is our maximum speed. It's not our maximum distance. It is our maximum speed, right? It's our greatest y value. So when I interpret this point, I want to make sure I include that this is as fast as she ever goes. So Beth's maximum speed is 10 kilometers per hour at 2.5 kilometers into the race. Or halfway through the race, you could say. Questions for me on number 2? Okay, go ahead and turn the page. And I want you to try number 3. There's some function notation stuff in there, which we've done before. There's interpret the x-intercepts in there, which we've done before. So I want you to try number 3. Okay, let's take a look at number 3. Find and interpret f of 3 in the context of the problem. So this means our x value is 3. So we go to where x is 3 and follow that to our graph. So f of 3 is 60, since 60 is our y value at that point. F of 3 equals 60. Now, our context of our problem is about the price of a soccer ball versus the profit that we make. So this would mean what? F of 3 equals 60. What does that mean in the context of my problem? $3 is the price of my soccer ball. And then how about the 60 part of it? Yeah. When a soccer ball costs $3, you make $60 in profit. For B, we're asking about the x-intercepts here. So right here looks like maybe just a hair over 2. And then over here between 14 and 15. So my x-intercepts, it actually didn't ask me what they are. It just asked me what they mean. So it saves me having to estimate this one at least. But this would be the price of a soccer ball that results in a 0 profit. So this is the amount I could charge for a soccer ball that would let me break even. Break even means I'm not losing any money, but I'm also not making any money. So the x-intercepts gives the price per ball that would result in $0 in profit. Oops, result in $0 profit. On the low end, that probably means that we're selling our soccer balls at cost. So we sell them for what it costs us to make them. At the high end, that probably means we've priced our soccer balls so high that we're not selling any, or we're selling so few that it just covers the cost of producing them in the first place. And then verse C, it says find f of x equals 120. So this time we know the y, and we're looking for that x value. So this is by 20s, it looks like. So here would be 120. It hits my graph here. And then also here, because we're a parabola. So this would be f of, looks like 4. And we'll call that 13. It's probably just shy of 13, but we'll call it 13. Equals 120. So what does that mean in the context of my problem? We're making $100 in $120 in profit when?
So price. Well, when the price for soccer ball is $4.
Yeah. Yes. We make $120 in profit when the price of a soccer ball is $4 or $13. Before we move on from this problem and talk about number 4, there's one last question I want to ask you that's not on here. What is the most amount of money that I could make from selling soccer balls? What's my greatest possible profit? What did you look at to find that? The vertex, right? That would be here at about 240. If I price my soccer balls, it looks like a little over $8. That's when I can make the greatest profit. Okay, and then finally, number 4. You are interested in retrieving a souvenir from a shipwreck at the bottom of the ocean. Your dive to the ship is shown in the graph below. So here's our distance below the water. So our water line here is right at the x-axis. And then this is the time of my dive. Down here is my treasure, or whatever it is. Okay. How long am I underwater? About 100 seconds. How did you find that? Yeah, we look at the x-intercepts from 0 to 100. That's 100 seconds. How far down is the shipwreck? About 125, right? I'm looking at the vertex. There's 100. It looks like these go by 10, so 120, 125. About 125 feet. What do the x-intercepts represent in the context of the problem? I know they're at 0 and 100.
Go down and then come back to the surface.
Yeah, the start and end of my dive. Those x-intercepts are where I'm breaking the water, right? When I go under the water and when I come back up. The x-intercepts represent times when you break the water's surface. Either to dive or to resurface. Those x-intercepts are times when I'm breaking a water surface. Questions for me for today? Okay, at this point, we have completed our quadratics review. So we will start exponential functions tomorrow.